Trio, Express or DNX? Does it sound familiar? In the next minutes, we'll explain the different types of packet forwarding engines present in Juniper routing portfolio, what we are developing, what we will use, where and why. In January 2022, an article has been published in the Juniper.net blog. Choosing a silicon architecture, it's all about finding the right tool for the job. This marketing slogan illustrates very precisely how we approach the network processing unit's development or selection in our routers. We'll split this video in 4 parts, starting with the key concepts on packet forwarding engines, memory and SERDES. Second, we'll describe Juniper Silicon, chipsets developed by our engineers. Then we'll present the third-party network processors we use in our portfolio. And finally, we will explain why we use one PFE type or another and where. Juniper offers 3 big families of routing devices. All of them are running Junos and can be automated with our Paragon software suite. A first dichotomy can be done right now. MX and PTX are based on Juniper ASICs, ACX is using merchant silicon. Well, if you pause a second and look a bit closer, you may discover that things are not so simple. Indeed, in the ACX you can find Juniper parts. For example, it contains a processor, the PTP FPGA, offering higher scale for timing. On the other hand, many constitutive components of the MX or PTX routers are coming from external suppliers. CPU, memories, microswitches, gearbox, SERDES, PHYs. The list is very long. But if you limit the categorization to the packet forwarding engine only, then it's accurate. MX and PTX are based on Juniper Trio and Express chipsets, and SEX7K are powered by Broadcom Jericho 2 variants. Let's try a different angle to categorize these PFEs, their architecture. Here again, we can sort them in 2 distinct groups. Please accept a certain level of simplification and abstraction in my description. We only have a few minutes in front of us. But we will present much more details in the near future. On the left, a massively parallel structure where each element can be programmed to handle the entirety of a packet treatment. On the right, a pipeline structure made of subsequent blocks. Each block performs one specific action, and it's the succession of these steps that makes the packet treatment. We will present these 2 different approaches one by one, starting from the most flexible, the multi-PPE run-to-completion architecture. In this model, the packet forwarding engine I'm using as a reference point is the Trio ASIC, you know, the one powering our MX routers. It receives and transmits frame and packets on 1 interfaces, and on the fabric side, it handles cells. The Trio architecture can be abstracted to 2 major subsystems. The MQSS connects WAN and fabric interfaces. It manages queues and packets buffering in memory. The LUSS performs all the packet processing tasks, lookup, classification, filtering, hashing, and all header manipulations. This subsystem is composed of a large matrix of packet processing engines or PPEs. Each of these PPE can execute multiple threads. The latest generation of ASIC, the Trio 6, can run 20 threads in parallel and is made of 160 PPEs. Generation after generation, Juniper engineers managed to pack more and more PPEs in the chipset. You understand here why we are talking about massively parallel architecture. Let's take a closer look at this PPE. It's a totally independent entity handling the entirety of a packet treatment. It deals with the packet headers or the full packet if it's a small one, and it doesn't care what's happening on the other PPEs. The information required for packet processing is stored in large memory banks reachable via a crossbar, and this can be done as many times as needed. A PPE executes a series of instructions describing the operations needed: parsing, lookup, encapsulation, rewrite, and many others. These instructions are written in an advanced but still very readable language, offering a lot of flexibility. The execution of this program may require a different amount of time depending on the number of instructions and their complexity. That's what we call a run-to-completion model. It takes the time it needs to perform the operation. That's why PPEs are totally independent from each other. If one needs more time to execute a complex packet processing, it doesn't impact other PPEs performing a simpler task. You can virtually implement everything, including protocols that don't even exist when the ASIC arrives on the market. That's typically the case for SRv6 or beer. When the head has been fully treated, it will be passed to an on-load block and then to the MQSS for transmission. Now, let's follow the life of a packet in a router at a very high level and see why this architecture is named a two-stage buffering model. We'll consider 4 different PFEs here. The bottom right will be our exit point, the others are receiving packets. Among these packets, one requires low latency queuing. The 2 others can be treated as best efforts. The first step of the process is a pre-classification defining the importance of each packet. Very useful in case of PFE congestion to guarantee the delivery of routing protocols update and keep alive mechanisms like BFD. Then, depending on the packet size, it can be split in 2 parts, head and tail. That's the first buffering stage in our architecture. The tails are stored in packet memory, on-chip or off-chip buffer. Heads are completed with internal data, and that's what we call parcels. The LUSS dispatcher will distribute them to available PPEs. At this moment, ingress features are applied and a lookup is performed to identify the egress PFE. Packet is reassembled by the MQSS, split into cells and transported to their destination over the fabric. Note that it's possible that packets are stored longer in buffers in the Ingress ASICs if the exit PFE is congested and requires the rest of the chassis to slow down via a back pressure mechanism. Now the cells are received on the bottom right, reassembled in packets, and then the process restarts a second time. Packets are split in head and tail if they are long enough, and parcels are dispatched to 3 different PPEs for egress treatment. That's the second stage of buffering in this model. If in our case all packets are targeted to the same egress ports, we may face a congestion situation, and the MQSS will decide what is the most important packet to be transmitted first. At that point, I would like to insist on an important aspect. With this model, the packets are stored in buffer physically present on the egress PFE. The queues are local, and we can implement extremely elaborated QoS features. When we present the number of queues available per ASIC, for example, if we say 128,000, it means we have 128K queues actually available to be shared among the egress ports physically mapped to this chipset. If I have multiple ASICs in my line card and multiple line cards in my chassis, the number of queues will add up. That means several million of queues per MX10K chassis. It may sound totally obvious to you, but I insist on this point because things are very different on other kinds of architectures, and that's what we are going to describe now with the pipeline model. A pipeline is a series of subsequent blocks. Each block is designed to deliver a specific task. It executes a microcode to perform this precise job. So it's programmable, but in a sense, it is specialized to deliver a certain result. For example, a block will take care of VLAN or tunnel termination, another will perform source and destination address lookup, another one will deal with the next hop information and how the load balancing can be done, or finally, another one will apply filters for classification or firewalling. Step by step along the pipeline, each block applies actions on the packet header, update internal fields and counters, and use pointers to indicate the next blocks what to do. In this design, the blocks are different between ingress and egress, and traditionally we have higher level of flexibility with more blocks in ingress than egress. To perform this job, each block can access different resources, that's memories or databases if you want, and it has a finite budget of access to read, write, or update information in this resource. So blocks are usually limited to a certain job, they are aligned in a certain order, and they can access information only a certain amount of time. Note that I'm saying usually, because inside each pipeline category, implementations can be totally different. But in a general manner, it's fair to say that it's not as flexible as the run-to-completion model I was describing a few minutes ago. With these specializations of role, actions can be executed very quickly, and the performance is also much predictable. You notice on the diagram some internal connections here and here. These interfaces can be used to re-inject the packets, or the header only, back to the entry point of the ingress pipeline. That way, a packet can be given additional treatment that was not possible in the first pass. It permits the implementation of more advanced features, but of course at the expense of the performance and bandwidth. In many situations, it's an acceptable trade-off if you know what you are doing and what could be the consequences. Okay, so the packets are received in the ingress pipeline and are treated in a succession of blocks. In the case of Juniper Express or Broadcom DNX chipset, they are split in cells. Cells travel through the fabric and are reassembled on the egress pipeline, where they will be treated by another succession of different blocks before the packet is transmitted. If the packet is received on one PFE and transmitted on a different one, it will use the ingress pipeline on the first, and only the egress pipeline on the second. Thank you, Captain Obvious. It's possible to have several pipelines in a given PFE, and we call them slices, or more logically, data path. Regarding the packet buffering, it's done in a memory reachable from the ingress pipeline. We call this approach Ingress-Only buffering. There is a small on-chip memory on the egress path, but the classification capabilities here are minimal and certainly not enough to apply any kind of QoS. Okay, we store packets in the ingress side only, but more precisely, how does it work? It's time to introduce the concept of virtual output queue. VOQs are virtual representations of egress ports and queues, but from an ingress PFE perspective. Indeed, to handle the congestion on the outbound port, we need to be able to differentiate the flows. But the queues can be created on the egress PFE since we don't have any significant buffer there. We need to create this construct on all ingress PFEs. Okay, let me try to illustrate this cryptic definition with a simple example. A packet is received on the top left port of this diagram. Destination lookup is executed and we identify the egress interface needed to reach the next stop address, XC030. Also, classification is done and packet is associated to a specific queue, number 4. A QoS policy can change this default behavior. The combination of the two, egress port XC030 and queue number 4, is the virtual output queue identifier, XYZ. Now, the ingress scheduler will inform the destination PFE egress pipeline that it has now 2 kilobytes of traffic with VOQ ID XYZ to transmit. And that's it for the first part of the job. Before I move to the second part, one word on VOQ scale. When we define a set of VOQ for a given egress interface, XC000, you don't know where the packet could come from. It could be potentially from any PFE. So we need to create this VOQ structure globally, everywhere on all PFEs. So the consequence is you'll have to instantiate the VOQs of all possible egress interface in all PFEs of the system. Since the VOQ pool is a finite resource, you are limited in the number of interface or IFL you can define. To put things slightly differently, the question, how many queues do you support on this networking ASIC, must always be completed by, are you talking about VOQs or queues on the egress PFE? Indeed, in the first model we described earlier, the number of queues were related to the number of PFEs present on the system. More PFEs, more queues. But in these ingress buffering architectures, the global number of queues of a router is limited by what a single PFE can offer, and this resource needs to be shared with all egress ports. And to be exhaustive in my explanation, some solutions exist to get more from this kind of architecture. For example, with mechanisms like VOQ localization, it's possible to split the resource in two parts, one group of VOQ ID to reach the destination PFE, and the rest of the VOQ IDs are only locally significant and describe local port queues. But since this information needs to be used in the ingress pipeline, it requires packet recycling. So it comes with a trade-off in terms of performance and bandwidth. The second part of the forwarding mechanism is based on a pool model. The scheduler in the egress pipeline receives solicitation from 3 different PFEs, and based on the QoS configuration, it can decide the order of token allocation. Those tokens are right to transmit for a specific VOQ ID and a certain amount of traffic. For instance, we have high priority traffic from the top right ASIC. The system will allocate a grant for 10 kilobytes for this particular VOQ ID. The PFE complies and sends the requested quantity of traffic towards the fabric. Again, in the case of Juniper Express and Broadcom DNX, it will be under the form of cells. These cells are reassembled, the packet treated in the egress pipeline, and eventually sent towards the destination on interface XC030. And we repeat the operation for all packets of lower priority. Among the benefits of such architecture, we store the packets only once in buffers, reducing the latency and the power consumption. Also, it eliminates the risk of head-of-line blocking. I want to insist on an important point here. I'm just describing architectures. That means they are following common principles, but they can still be very different. Indeed, the number of blocks in the pipeline, in ingress or egress, how programmable they are, the type and size of the resource they can access, the budget to access it, the internal shortcuts inside this pipeline, and many other aspects could lead to different capabilities and different scales. Now, a quick summary of the pros and cons of each model. And to make things simple, I'll say the cons of each architecture are simply the fact that they are not the other one. A pipeline cannot achieve the same flexibility and the same number of queues than a multi-PPE run to completion where we do egress buffering, itself not able to offer the same performance and power consumption that the first one. Before moving to the chipset specific description, I would like to briefly touch on two important points, the packet memories and the SERDES. The memories first. I'm not taking too much risk stating that every modern packet processing architecture is now using some hybrid buffering approach. In normal conditions, the packets are stored on an on-chip SRAM. It's a fast memory dimension to handle line rate traffic on all the PFE, and in case of congestion, some queues and packets can be moved to a larger memory space we call an off-chip buffer. And these memories are usually much larger than internal SRAM. But also it's interesting to note that we purposefully oversubscribe the bandwidth to off-chip buffers. The systems are not designed for all ports congested at the same time. It's something that you can create in a lab, but it makes no sense in production networks. So we are talking about off-chip memory here and not off-package. And it's true for most systems leveraging HBM. HBM stands for high bandwidth memory, and they are offering indeed a very wide bus, 1000 bits, and low power consumption. The SDRAM stacks are in the same package, but on the side of the forwarding die, and they are interconnected through an interposer. So HBM can be used for packet processing, of course, but not only. We can store prefixes, flow records, statistics, and many other types of processing informations. Nevertheless, we will still see some systems with graphical memory, like GDDR6, scattered around the PFE. Most of the time, they are low bandwidth routers. Now, a quick word on SERDES. The PFEs, and more precisely the port groups and port macros, can use different modes of operation with different number of lanes, 1, 2, 4, or 8, different encoding schemes, non-return to 0 or 4-level pulse amplitude modulation, and different speed as listed in the examples of this chart. These capabilities and how we can mix them will have important implications on the type of optics modules supported by a given PFE. We will come back on this with a concrete example in a few minutes. Now, let's talk about ASIC development in Juniper networks. It's a very long tradition that started in the late 1990s with the M40, the Martini. During the first decade, we have seen multiple trends: the reduction of the number of chips constitutive of a PFE, and in parallel, clock frequency increased significantly while voltage requirement was reduced. In these first 10 years, the space occupied on the PCB stayed more or less constant. During the second decade, we completed the consolidation into a single chip PFE and introduced the concept of slice. Also, in the same period, we reached a plateau in terms of frequency, around 1 GHz. To allow performance growth, we have to use larger footprint on the PCB. 2020 marks the beginning of the system-in-package era, with multiple dies, multiple slices, and multiple heterogeneous elements in the package. A bit too early to say more, but indeed we are talking about chiplets here. Let's take a look at the evolution of the Trio ASICs used in the MX series. The first Trio PFE has been introduced in 2009, and it offered at that time up to 70 gig per second. Every 2 or 3 years, a new version was released, supporting more interface types and improving capabilities, bandwidth, and power consumption. The very latest member of this family is the Trio 6, 1.6 terabit per second full duplex ASIC, optimized for 400 gigabit Ethernet and natively supporting MACsec line rate on all interfaces. We are talking about a multi-PPE run-to-completion ASIC here. So, in essence, it can serve all roles and offers the highest scale in FIB, RIB, VRFs, filters, and queues. Since it's a two-stage buffering design, these 128,000 queues are present on egress and for all ports mapped to these PFEs. That's why it can deliver advanced QoS and subscriber services. Today, the Trio 6 is present in the LC9600 line cards in the MX10K chassis. 6 PFEs per line card for a total of 9.6 terabit per second per slot. And it's also coming in the MX304 in a couple of months. It's a 2RU system with 2 or 3 interface cards, each one hosting a Trio 6 PFE. Again, all features are virtually possible on Trio-based systems. It's the most flexible and programmable architecture in our portfolio. More pragmatically, if you purchase an MX system for a specific role today, you don't have to worry about changing your mind and asking for more in the future. It can do it all. Juniper Networks is also developing a second family of chipsets used in the PTX routers, the Express ASICs. Launched in 2012, the first Express was a 120 gigabit per second chipset. The current shipping version is Express 4. It powers the LC1201 or LC1202 in the PTX10K chassis, but also the PTX 10001 36MR. It's a 3.6 terabit per second forwarding engine with integrated MACsec and a lot of very advanced capabilities in terms of routing scale, sampling, filters, telemetry, and statistics. We already announced the next generation and it will be a huge evolution. Express 5 already taped out in January. That means the design phases are completed and it's now moved to fab. This ASIC is a 28.8 terabit per second package optimized for 400 and 800 gigi with line rate MACsec. 800 gigabit Ethernet, that means we are supporting 100 gig SERDES. But it's not only much faster. It provides significantly higher scale and also new capabilities like SRv6 and SPEAR. Without going into too much detail, here is a high-level view of the Express ASIC pipeline architecture. I will just insist on the arrows here. They are representing a very unique feature of the Express pipeline. The circle arrows, it represents the capability to keep the header for multiple cycles if it requires additional treatment. That means the block is not necessarily limited by a fixed clock and could offer more flexibility than some other designs. Between filter and destination lookup, you can see it's actually a bidirectional arrow. That means the headers can go back and forth between these two blocks. It helps implementing spatial treatment and filtering in specifically complex tunneling use cases. Finally, I'll mention this arrow here between filter block, ingress and egress pipelines. That one gives us unique filter scale. You certainly noticed that each new generation offers a big jump in bandwidth and connectivity. It's true for Trio, but it's even more sensible for Express chipset with a very impressive 28.8 terabit per second on Express 5. But the innovation is not only about bandwidth and support of 400 or 800 gigi, it's also about the features we can deliver with these chipsets. For Trio, it's a very easy picture to draw. It's the most flexible and programmable PFE in our portfolio and can do everything, including complex management features with BNG and 5-level hierarchical QoS. For Express, the feature coverage and scale improve generation after generation, and therefore it extends the role the router can cover. But you can see on this chart that some features are difficult to reach and will only be available on Trio-based systems. Let's be clear, nothing is completely impossible, but it could come with trade-off that will not make the use case economically viable. Could it be because it will require the addition of specific memories, or because it will imply multiple packet recirculation impacting the performance? Some architecture, like run-to-completion models or two-stage buffering, are more suitable for certain roles and don't require trade-off. It's interesting to note that some innovations developed on one architecture have been leveraged on the other one. For example, the FLT block or the MACsec engine. Now let's move on to the third category of PFEs, the Broadcom DNX used in the SERDES series. With the latest Juniper Silicon, we have a run-to-completion chip of 1.6T, highly programmable and scalable, and an optimized pipeline ASIC of 3.6T and soon 28.8. So we can design products with bandwidth requirements that are multiple of these numbers. But what about situations where you'll need much lower bandwidth, or if the requirement is in between? Certainly, you can think that those who can do more can do less, but it's not always economically true, and it becomes totally wrong when we talk about high density of low-speed interfaces like 1 GigE or 10 GigE. So we need more flexibility to address aggregation roles and also for the customers asking leaner edge capabilities. That's where the Broadcom DNX can give us a lot of options. In early 2022, we already have a couple of routers equipped with Jericho 2 and Jericho 2C, respectively the SEX 7100 and the SEX 7509. So we can leverage the other DNX chipset of the same generation for lower speed, like 1.6 Tera, 800 gig, 360 or even 80 gig. Or even for higher bandwidth too, with Jericho 2C Plus at 7.2 terabit per second, and future Jericho 3 and Qumran 4. Any new product based on these ASICs will benefit day one from all the development efforts invested on the J2 platforms. So in a nutshell, it will give us flexibility to offer systems with bandwidth and port density that were not optimally covered by the Juniper Silicon options. The DNX family is based on a pipeline architecture. That means ingress buffering only on a VOQ-based scheduling mechanism. Also, it follows a hybrid buffering logic with on-chip and off-chip packet memory. On the lowest bandwidth variant, this off-chip memory is not an HBM, but a GDDR6 scattered all around the ASIC. Some interesting features are offered by the DNX architecture, like the elastic pipeline, permitting specific logical operations programmed in C++. So there is this large variety of DNX options, and how do we select one or another for a specific requirement? Different parameters can be used to compare them and drive the selection process. Of course, the bandwidth is a key factor, but also you have to ask yourself, is it a standalone system based on a single ASIC, what we call a SoC or system on a chip, or will it need fabric to interconnect to other PFEs? Does it offer built-in services like MACsec or timing? What is the VOQ scale? Remember that by default, this VOQ resource is global to a chassis and must be shared between all egress ports. How large is the stats resource? And what about the database used to store processing information? Jericho 2 introduced the concept of modular database. This MDB is a large memory pool that can be carved during the booting process to allocate space needed for specific roles. So for example, for L2 VPN specialized router, we'll allocate more LEM, and for L3 VPN, we will favor the LPM. And it can be configured on the router via MDB hardware profiles. Another very important parameter to guide the ASIC selection is the type of port macro it offers. The PM is basically a group of SERDES used to interconnect the PFE to the rest of the system. On the PM25, Falcon, we can configure SERDES speed from 1 to 25 gigabit per second. So it permits connectivity to ports from 1 gig Ethernet to 100 gig Ethernet, like SR4 or LR4. On the PM50, Blackhawk, you can configure SERDES speed from 10 to 50 gig. That means you can enable interfaces up to 400 gigabit Ethernet. You understand here that you can't offer 1 gigabit Ethernet on PM50, and you can't get 400 gigabit Ethernet on PM25. And finally, you can have a port macro with a supported range spanning from 1 gigabit Ethernet to 400 gigabit Ethernet. On this chart here, you can see the different PMs used for each chipset, and you can derive what you will need for the role you try to address. For example, for 1 gigabit Ethernet, Jericho 2 cannot do it natively. It will be best to use Jericho 2C. Do you understand the logic? Finally, for your reference, I'm presenting two last parameters to compare DNX chipsets: the number of VOQs and the number of counters. As explained before, the VOQ pool is a resource shared globally, and you need the largest possible for a system with a large number of interfaces like chassis. On the statistics side, to help draw a comparison, the Express 4 and 5 have a memory supporting up to 8 million counters, so that's 20 times more than Jericho 2X, 2C and 2C+ here by default. Note that you can extend that number with an additional FPGA or external TCAM. Now let's move to the last part of this video: what makes the more sense and where. I hope the motivation behind the use of DNX ASICs has been clearly explained in the previous section. It fills the gaps we have in terms of bandwidth and port density. Also, item capability and small footprint make it a great fit for access and aggregation use cases. These ASICs support the latest transport and service technologies, like SRv6 and EVPN, with low latency and a very decent scale. Therefore, they can be used in multiple places and roles. Based on a massively parallel architecture of run-to-completion PPEs, the Trio ASIC is the most programmable and scalable chipset in our portfolio. It can do it all, including features like BNG and 5-level hierarchical QoS, aggressive sampling rate for specific security applications, deep packet parsing for advanced load balancing, corner cases like high-speed fragmentation and reassembly, and very specific applications like the optimization of machine learning clusters. With the latest Trio 6, we are powering 400 gigabit Ethernet line cards and multi-terabit fixed systems. Of course, the Trio development continues, and the next generation is already under preparation. That's the investment protection chipset by excellence, and we have a very successful track record with the MX chassis. With Trio platform, you can deploy for a specific role and change your mind later because it supports everything needed today, but also it's ready for the not invented yet. Express PFEs are optimized for specific features and roles. So generation after generation, we extend the range of supported interfaces, the performance, more bandwidth and PPS with lower power consumption per gigabit, but also the feature coverage. The next generation we already announced will support 800 gigabit Ethernet interfaces and an impressive 28.8 terabit per second forwarding capability. So it's a pipeline architecture with ingress buffering and VOQ logic, offering lower scale queuing capabilities compared to Trio, but some unique features and scale differentiated from other pipeline architectures. 10 million prefixes, high scale filters, large counter memory, unlimited next-stop recursion chain, adaptive load balancing, and many more that makes the Express-based platforms very optimized products for core, peering, and DCI roles. So in conclusion, here at Juniper, we don't believe in a one-fit-all approach for routing silicon. Certain requirements are better addressed with specific architecture. And that's reflected in our development and investments. The right tool for the job. Thank you.